Thank you very much. And let me see. I don't remember if I switch on. Yes. First of all, I would like to thank the organizers for inviting me to this very nice place and to very interesting workshop. And my talk, I must say that my talk does not contain any rigorous mathematics, just a numerical result. I consider a very simple problem, the collisionless gas. This is the simplest kinetic equation. And since I'm getting old, so I don't want to do complicated things. So just a simple thing and only numerical. And it contains two topics. And if I have time, I enter a little bit the third topics. First one is approach to equilibrium of a collisionless or free molecular or Knudsen gas caused by interaction with the vessel wall. So this is a joint work with my PhD student Tetsudo Tsuji and François Gauze. And then the second problem is the decay of an oscillating plate in a collisionless gas. This is a joint work with Tsuji. And the third one is approach to steady motion of a plate in a collisionless gas. So joint work with Tsuji and Guido Cavallaro from Rome. Okay. So what is collisionless gas? This is very simple. So, if the gas is highly rarefied, then the mean free path is infinitely long compared with the characteristic length of the system. In that case, you can neglect the effect of collision. Okay? So the Knudsen number, which is the ratio of the mean free path to the characteristic length of the system, is infinitely large. So in that case, you can just drop the right-hand side of the Boltzmann equation, and so you have a very simple transport equation, free transport equation. And so even not Vlasov, because we omit the external force. Okay? So then here F is a velocity distribution function of a function time t position x and molecular velocity c, and then you can immediately write down the general solution of this equation, namely the F is constant along the characteristic or physically the trajectory of the molecules. More precisely, if you are at time t as in the position x and you look at the value of F for the velocity c, then it is the same as the value of the F at time t0 and this position and for the same velocity c. Okay. And in the time independent case, also the solution is written in this way with the parameter s. So this means that F is constant along the straight line in the direction of molecular velocity. Okay. So this is a very simple solution. So if you use this general solution, then immediately you can write down the solution of the initial value problem in the infinite domain with initial data g. Okay. So the solution is just g with x replaced by this quantity. So this is the solution. And if you consider a steady boundary value problem, time independent boundary value problem for the single convex body in the infinite expanse of gas, then also the problem has already been solved practically, because in that case you specify the velocity distribution function at infinity, and also you specify the boundary condition, which in general gives a relation for the impinging molecules between the impinging molecules and deflected molecules, xi dot n positive. Okay? So if you consider the point on the body, then you know all the incident molecules, all of them are coming from infinity because the body is convex. So you can compute, you know, the incident flux. So you can compute using boundary condition, the distribution function for reflected molecules for any place. Therefore, if you are here, then for such molecules, you just trace back and you take the value at infinity. So this is constant, and constant along this line. And for such molecules, you trace back and you hit the boundary, then you pick up the value at the boundary for reflected molecules. So practically, the problem has been solved. So it's very simple. And for general boundary, if you have non-convex body or multiple bodies, then or boundaries, interior domain, then things are a little bit complicated. If you consider this point, and you want to compute the velocity distribution function for reflected molecules using a boundary condition, then for such molecules impinging in that direction, you trace back to the infinity, then you know the velocity distribution function. But for such molecules, you don't know. You should put the velocity distribution function for reflected molecules at this point. So practically, this relation boundary condition gives the integral equation for the velocity distribution function for reflected molecules. So just you needed to solve this, and then everything. So it's simple. Okay. So now I want to explain the conventional, the usually used boundary condition for the Boltzmann equation. Here, in general, you have to specify, or more or less specify, the velocity distribution function for reflected molecules on the boundary. So, namely, C minus VW dot n positive. Here, VW is the local velocity of the boundary, and so this is reflected molecules. The simplest boundary condition is a specular reflection. So, just molecules are reflected specularly on the surface. So, just the normal component is inverted. Okay? But this is too ideal, too singular, I say. So, the most widely used and the simplest and more realistic boundary condition is the so-called diffuse reflection. So in this condition, the reflected molecules are assumed to be distributed according to the Maxwellian distribution with local temperature Tw and velocity Vw of the boundary. Here you put the boundary temperature and the boundary velocity. Okay? Then R is the gas constant. And then here is the density of the Maxwellian. This is half-range Maxwellian. But you don't specify the density. Instead, you impose the condition that there is no net mass flux across the boundary. Then this sigma W is expressed in terms of the flux for impinging molecules, like this. A bit complicated. So this is the usual boundary condition. Then more sophisticated, this is also classical boundary condition is the diffuse Maxwell type condition. This is very classical already. Maxwell used this condition. This is a linear combination of diffuse reflection and specular reflection, and this coefficient alpha is called the accommodation coefficient. And more recently, or recently means compared with Maxwell type, already 40 years ago, Chelchinian and Lampis proposed the more sophisticated boundary conditions. And at that time, it was too complicated to use this boundary condition. But nowadays, for numerical analysis, no problem. So now, many people are using this condition. This is more sophisticated condition, but I omit the details. Then, so here I want to consider the initial and the boundary value problem. Okay? So first problem is approach to equilibrium of collisionless gas. So for the moment, forget about collisionless gas, the usual gas. So you have a container and with fixed temperature, constant temperature, Tw, uniform temperature. Then you put the gas inside. Then you disturb the gas. Then you leave the box for a long time. Then the gas tends to approach, should tend to approach the equilibrium state given by this Maxwellian. That is, the temperature should be the same as the temperature of the boundary, and zero mean velocity, and the density is given by the average density of the initial state. Okay? So this is very physically this is obvious fact, and this has been the important subject for the Boltzmann equation with collisions. Okay? So there are many studies like Glad, Chelchinian, and more recently Devillet, Villani, Yang. So in particular, Devillet and Villani considered the specularly or backwardly reflecting boundary box contained with such boundary condition or periodic box, and they showed that the approach to the final Maxwellian is faster than any inverse power of time. Okay, and so here the final Maxwellian is different from previous one because these boundary conditions does not have a summarizing effect. So the temperature, instead the energy is conserved. So the temperature is determined with the energy conservation from the initial condition, as in the case of density. And for periodic box also, if the initial condition has momentum, then the final Maxwellian can have average velocity, but this is a trivial case. And also the measure of this distance between the distribution function and the final Maxwellian is a kind of measure is given by relative entropy. This and this decay is faster than any inverse power of time. Okay? And so this is important work. This is one of the reasons of Cédric Villani's winning of the Fields medal. And sometime later, Cédric Villani extended this proof to the case of diffuse reflection, rather recently. And the same is true, same decay rate is true, but the final Maxwellian is the previous one, the Maxwellian with the same temperature as the boundary. Okay. And also recently, Yang shows the exponential decay when the initial condition deviates slightly from the initial state. So the final equilibrium state. So small deviation from equilibrium state. Okay. Now, now I want to consider the case of collisionless gas. So now there is no collision inside the gas, so there is no summarizing effect. But still, the molecules interact with the boundary, and if the boundary has a summarizing effect, then it should also the gas should approach the final equilibrium state with the same temperature with the boundary and the mean velocity and some specified density. Okay, and in fact, this convergence to the equilibrium has been proven by Alkelid and Nuri, and with a diffuse reflection condition. And more precisely, they showed the convergence to the stationary solution with arbitrarily distributed temperature of the boundary, but this contains this decay to the equilibrium. Okay. And in this case, this proof does not say anything about convergence rate. And so in this case, the very slow approach to the final equilibrium state is expected. So something like our guess was like this. Okay, the distance, appropriate distance between the F velocity distribution function and the final Maxwellian is something like decay, something like inverse power of time, and this exponent D is the dimension of the box. Okay. So this is our guess, and we wanted to show some numerical evidence of this guess. Okay. So I start with the simplest 1D box, namely it's a slab. Okay. So the same temperature, uniform temperature, and physical quantities do not depend on the coordinate along this direction. Only it depends on x. So so this is 1D transport equation. Cx is the x component of the molecular velocity, and some initial condition and boundary condition. This is diffuse reflection. A bit complicated. So. Say on this boundary when x equals 1/2. Here I non-dimensionalized all the quantities. So the distance is 1 and temperature, this quantity is 1, so on. So at the boundary, this boundary at x equals 1/2, then you specify this upper sign. Please take upper sign. You specify the velocity distribution function. This is Maxwellian with the wall temperature, and density is expressed in terms of the F for impinging molecules. And if you just you formally write down the solution of this, then you get this F for the x component of the velocity with this range. That's a slow velocity. It comes from the initial condition. Otherwise, it comes from the boundary. But you don't know this boundary because this sigma W plus minus is unknown. And schematically, so like this. This is the xt plane. So suppose that you are at point x and time t, Then if you choose one, if you consider the velocity, molecules with velocity, if you choose the velocity of the molecules coming at this point, then this determines one straight line, and the gradient corresponds to the velocity. For such molecules, this is rather slow molecules. Vertical molecules are slow, so molecules come from the molecules in this range come from initial condition. So this is this interval. And otherwise, the molecules, faster molecules come from either left boundary or from right boundary. And if you try to compute this density, deflected density of the diffuse reflection at this point, then you need information for all impinging molecules. For the molecules coming from here, you get you take the information from initial condition, but for there you need the information for the other density for the other boundary, sigma w minus. Then this gives the integral equation for sigma w plus and minus. In particular, this is the MT, the source term is from the initial condition, and the kernel R is this form. And if you consider the case where everything is symmetric with respect to the origin, like you give a symmetric initial condition, and then in that case, sigma plus and sigma minus at this point are the same. So in this case, this is simplified, and you get so the sigma here, sigma w denotes either sigma plus and sigma minus. Then you get a single equation for sigma w, and this is a linear equation that François Gauss mentioned yesterday, and it was studied. The asymptotic behavior was studied by Feller already in 41. And so this is source term coming from initial condition, and the kernel is like this. And once you get sigma w from this equation, then you obtain velocity distribution function at any point, and then you can compute all macroscopic quantities. So we solved this numerically, because there is a result theorem by Feller, but his theorem was not sharp enough to see the decay which we wanted to see. So we tried to solve this equation numerically, and so the numerical solution of this equation is very simple, 1D integral equation. However, to see the decay rate, you have to do a very long time computation, and also you have to see the very small quantity because it is decaying. So this is the difficulty of the computation. And so I show the result. And so also here I show the result with a very simple initial condition. That is, the initial condition is also Maxwellian, but with different temperature. So T0 is the dimensionless temperature. This is a ratio of the temperature of the initial stage to the temperature of the boundary. So 0.5 and 0.8, the original gas is cooled, and then it is heated by the boundary. These are opposite. In 1.2 and 2, you start with a hot gas, and then it is cooled down by the boundary. Okay. So this is a numerical result for a long time, and this is here. It's a relative entropy, but it is integrated only over the molecular velocity space. So it's a local. It's a function of the position. Okay. So local relative entropy. And so the initial condition is the temperature ratio is 2. So the original gas is hotter. Okay. And this is the plot of the W against T logarithmic scale, both. And this logarithm is a logarithm, common logarithm with base 10. So 4 means the time 10,000. And so there, the x equals 0 is the center, and x equals 0.49 is close to the boundary. So we, at the beginning, there is a difference, but then these lines tend to approach a single straight line, and if you measure the gradient of this line, then this tends to approach -1. So this means that W tends to decay like this. Okay, this gives a numerical evidence. But if you look at the density, density decays 1 power faster. This is density. Density goes to 1. and again the log plot. And then this is the density variation at this point with different initial conditions. So all the curves tends to approach straight line, and the gradient tends to, in this case, -2. So this means that density decays like this. But temperature decays like W. Like temperature at this point decays because the gradient of these curves tends to approach -1. Okay. And so this is the numerical values of the gradient at the time 10,000. So with different initial conditions, and for instance, W, the relative entropy at this point, and the other point are almost the same. At this point, the gradient is almost 1, and also this is L1 norm of between F minus F final Maxwellian. Then almost 1 and temperature 1, but this 2 and 3. So this density and velocity change decays in a different power. But anyway, on the whole, we can say that this difference between the velocity distribution function and the final Maxwellian tends to decay, like 1 over t in the one decays. Okay? So this gives some pieces of numerical evidence. And the next I show the behavior of the velocity distribution function. Okay, now I consider marginal velocity distribution function integrated over the molecular velocity component parallel to the boundary. Okay. So it is a function of time t and the position x and the molecular velocity x component cx. And I show the time evolution of g as a function of cx at time position x equals 0, the center. Okay. Okay. So this is the black curve indicates the initial condition, and this red curve is final Maxwellian. So the initial temperature is higher. Then the evolution of F is like this. And the molecule with velocity 0 never thermalizes because it does not reach boundary. Like this. So this part gives a slow decay. Okay. Next I show the other. So this is the next is not in on the center. The point rather close to the right boundary. Okay. So this part changes first, and then gradually this part changes. And then so this evolution is not very obvious. In this way, it decays. Okay. Okay, then 2 decays. And so here we have cheated a little bit because in the general 2D cases it is rather difficult to compute. So we consider only the circular cylinder. The 2-dimensional box is an infinitely long circular cylinder, and also the initial condition is the same as before, uniform Maxwellian with different temperatures. So in that case, the good point is that in general, if you consider 2D case, then the sigma, the density of the reflected molecules, are the function of the position on the boundary. But in this case, it is only the function of time because of thanks to symmetry. So then you get the similar linear equation as before. Here I have already taken into account the initial condition. So you have this source term, and again the kernel are like this. So it contains a bit complicated modified Bessel functions. But anyway, we can analyze this numerically. And 2D case, the result is like this. So again, this is a local relative entropy, and at 3 different points, and the initial condition is the temperature is twice as high as the boundary temperature. Then this log plot shows that after some time, the curve tends to approach the straight line, and if you measure the gradient, then it tends to approach -2. So this means that the decay is like this. Yeah? And again, the density decay is 1 per faster, and the velocity again 1 more. But the temperature decays like 1 over t squared. So this is the same as the case of W. Okay? So this is a decay of the temperature with different initial temperatures at the decay at this point. The radius is 0.2. The cylinder is radius at 0.5. Anyway, I skip the. Okay, so these are numbers at the maximum time. So we have done more computation, but taking the gradient is very difficult. So we have observed some oscillations. So we cannot show the reliable numbers. For the graphs, for instance, in W, we can show the curves until 10,000, but to show the numbers, at most, we can show the reliable numbers at this time. Because the 2D case, to obtain macroscopic quantities or integration is more difficult numerically. Okay, so anyway, we are able to provide some pieces of evidence which shows this decay when d equals 2. Again, it's a tedious repetition of the similar things. I should be quick. The 3D box also I consider only the case of the sphere, the uniform initial condition. So completely things are spherically symmetric. So the density of the reflected molecules are the function of time t. It does not depend on the position of on the boundary. So in general, this depends on the position in the surface. So it is much more computation becomes much more complicated. But in this case, the more or less the computation load to solve this equation is the same as 1D case. Then in the 3D case, so mt includes some exponential function, and the kernel is expressed in this way. So then a numerical result shows again a similar curve, but the gradient, if you measure this is W local relative entropy or free energy, and if you measure the curve, then it tends to approach -3. So this means that W decays like this. So density decays faster, but temperature decays like W. Okay. So and the 3D case, it is more difficult. We are able to show only the reliable gradient value of the gradients of this log plot and up to the time 1000. But anyway, we investigated the decay approach to equilibrium of a free molecular collisionless gas, and we are able to provide some pieces of numerical evidence which shows this decay rate. Okay, for 1D case, 2D case, 3D case, and 2D case only the circular cylinder, and 3D case only sphere, and more precisely uniform initial data. But for 1D case, we have also computed with a non-symmetric initial condition, and we confirmed this formula. Okay, so this slow decay is caused by of course, it's a slow molecules, which it takes for slow molecules, it takes a very long time to interact with the boundary. So this produces some kind of long memory effect. And there is another kind of long memory effect which is caused by the recolliding molecules. So I will come back to this subject later. Okay, anyway, there is one related work by Debret and Salvarani. So they consider the transport equation, and but in some zone in space, in some zone, they switch off the collision, and some part no collision, and some part with collision. And if the collisional domain shrinks to the surface, then it should be the result should be the same as the present case. So it would be interesting to think about. Okay, a small theoretical consideration. And so we are now considering this decay to the equilibrium of the collisionless gas with diffuse reflection boundary condition. Now, as I said, there is a proof of this convergence by Aoki and Nuri. And they proved the convergence of F to this final Maxwellian in this L1 space. Here they integrate this difference over the domain, space domain, and also n is 3. They consider only n is equal to 3, and molecular velocity space, and also in the time interval. So they consider the time interval from 0 to capital T, and then they consider they move the window like this to consider the long time behavior. Then they showed the convergence in this L1 node. And so there is a proposition by Francois Gauss. Suppose that there is a time decay rate E, which is independent of the initial condition, which satisfies this, namely the difference between F and the final Maxwellian is this L1 norm used by Aoki and Nuri is controlled by the LP norm of the initial condition with this decay rate. So suppose that this is true for any initial condition, then this decay function must satisfy for a long time this inequality. So when n equal larger than or equal to p, then this result is consistent with our numerical result, because n is a dimension, and so this just the edge is the same as the numerical result. Okay, so the proof is very simple, I say. So you choose just a special, since we have assumed that that inequality is true for any initial condition, then you choose just one special initial condition which allows mass concentration at point 0 and molecular velocity 0. Okay? So like this 1A is the indicator function of set A, and B is a closed unit ball of space, and so you put the epsilon small parameter, then if you extend the height with this 1 over the power 2n over epsilon, then this gives a mass concentration, okay, at point 0 and 0 molecular velocity. Then with this you can compute immediately the LP norm of this initial function, and then you can also estimate the left-hand side. You can estimate the left-hand side of this inequality from below by using the explicit solution. Then you get this. Now, okay. Let me move on to the second subject. Okay, this is again the initial and boundary value problem of collisionless gas. So the problem is decay of oscillating plate. So you have a plate, disk, and connected with spring. Okay, so this oscillates only. Suppose that it oscillates only 1D in the direction x, like this. And so this is the equation of motion of the disk. You have the acceleration, m is the mass of the disk, and this is the external force which obeys. We assume that which force obeys the Hooke's law, like this. X is a displacement. So now the spring is compressed. So this is the equilibrium position and displacement, and so in that case force acts in this direction, and this is a drag exerted by the gas, surrounding gas. So if the drag is proportional to the velocity of the plate disk, then it's obvious that this is very simple ODE, and you have oscillation, but the oscillation decays, amplitude decays exponentially in time. Okay? But the problem is what happens when the gas is free molecular, okay, collisionless gas. And as time goes on, the displacement as well as the velocity goes to 0. Okay. In fact, this problem has been already studied by mathematically by Caprino, Cavallaro, and Marchioro, people from Rome. So they they investigated the decay rate, and so they assumed specular reflection rather than diffuse reflection, and they consider a very special case. The mass is very close to the mass of the plate. Mass of the disk is almost the same as the gas. So this is like a balloon, very light. And then small initial displacement and small velocity, initial velocity. Then they showed that they proved that there is a case in which there is no oscillation. The decay is monotonic. So in that case, they were able to show the decay rate rigorously. Okay, like the displacement decays by the power t power d plus 2, and d is the dimension of the disk, and the velocity decays faster. Okay, so then from this, our guess was that if we use the boundary condition, diffuse reflection as the boundary condition, and if you consider even for non-small initial displacement and initial velocity, we should have the decay rate like this. Okay, the power changes because of the change of the boundary condition. Okay, so we investigated this problem numerically, and we have done only 1D case in this problem. So 1D case. So this is disk is a infinitely wide plate, and so 1D free transport equation and the initial condition, which is the Maxwellian with temperature T infinity and zero mean velocity and density rho infinity. And I assume the diffuse reflection condition on the plate. We assume that the temperature of the plate is the same as the temperature initial gas. Then the plate, the equation of motion for the plate for unit area of the plate is this equation of motion. M is the mass, and F is the force, which obeys Hooke's law, and D is the drag. And this drag force is expressed in terms of the velocity distribution function on the left face of the plate and the right face of the plate. So from this distribution function, you can compute the momentum transfer, and you can compute the drag. So then initial condition of the plate, initial displacement, and initial velocity, okay, of the plate. So these two systems are coupled through this drag force, because this contains F, and also the boundary condition because this contains the velocity of the plate. Then we solve this problem numerically, and so this is we have to obtain this trajectory. But suppose that you have already obtained this trajectory, you are here. This is a x and t plane. So as time goes on, this decays like this. Okay? And so again, the velocity distribution function is constant along the characteristic. So now we suppose we consider the molecules in hitting the plate at this point, time this position and this time. Okay? So so this gradient, this line indicates this gradient. The gradient of this line indicates the velocity of the plate at this point. Okay? So then, if you consider the molecules hitting the plate from the right, then these molecules correspond to these lines, and the molecules hitting from the left corresponds to these lines. Okay? And if you choose one velocity of the molecules which are hitting from the left, then suppose that molecules are determine such lines, then if you trace back, then you reach the initial condition, then you take the value of initial condition. Okay, so this is simple. But if you consider, if you choose such velocity which are hitting, molecules are hitting from the right, then if you choose such velocity, then if you trace back, then you meet the trajectory in the past. So this means that the molecules are already reflected on the plate at this point, at this time. Then this comes, this hits the plate again. So we call this recollision. Okay? For this, the molecules coming from such direction, also here, undergo recollision. Okay. Then this is a numerical result. So the parameters, the mass is 10 and the initial displacement is 1 and the initial velocity of the plate is 0. So this is very light plate because the mass is 10 times of the gas, so almost a balloon. But otherwise it makes many, almost infinitely many oscillations. So it's impossible to compute. And this is the double logarithmic plot of displacement against time. Okay, so at the beginning, so it oscillates, but at certain point it stops oscillation and then it tends to approach straight line. Okay, and if you measure the gradient of this line, then gradient tends to approach -2. So this shows clearly the decay rate of this displacement. Okay, so other case, this blue curve is a case where when the mass is the same as the mass of the plate is the same as the gas, so it's really balloon. In that case, there is no oscillation. Okay? So this corresponds to the mathematical proof by Caprino, Cavallaro, and Malchior. And this red curve is the same mass as mass 10, but the initial displacement is small, but still many oscillations. But in any case, all these curves, the gradient of all these curves tend to approach -2. So this means that you expect such parallel decay of the displacement. Okay? So this is a case of diffuse reflection. Of course, if you assume the specular reflection, then which corresponds to the proof by Caprino, Malchioro, Cavallaro, then this exponent should be -3. But numerically, the specular reflection is more difficult. Mathematically, for mathematical proof, it's easier. But numerically, it is more difficult. Okay, so next, this is the single logarithmic plot. This is the logarithm of displacement, and this is just time. In the same case, the same result as before. So it oscillates and then it comes like this. And what I wanted to show here is so what happens when the recollision is completely neglected. So you assume that all the molecules are coming from initial condition. Okay, so what happens in that case? So this is from this figure, it is ridiculous. So you cannot cross the trajectory in the past. But in reality, the many computations in the free molecular flow, the motion in the free molecular flow has been done in that way. So you chalk. Oh, I don't find. It's not a problem. Here. Wait. Oh, okay. No problem. Just so you fix the boundary, the body, and then you compute. You assume that all the molecules are coming from infinity. Then you can compute all the reflected molecules from the boundary condition. Then you can compute all the force and the torque acting on the body. Then for a small time step, you slightly move the boundary, and then again you compute all the fluxes from assuming that the molecules coming from infinity and so on. This is the usual. Usual way, but it is wrong because it does not take into account the recollision. It is correct only when the motion is steady. Okay. So if you do so, then what happens is, so decay is exponential, okay, clearly, and so this slow decay is caused by the recollision, okay? And this recollision gives a long memory effect because at the beginning the molecules are deflected by the plate, but it can hit the plate long time later. So this transmits the information at the very beginning to the very long time later. So this gives a long memory effect. And also in the case of exponential decay without recollision, it oscillates infinitely many times, and then the amplitude decays. However, in this case, with a recollision, algebraic decay, then the decay at some point, the oscillation does not cross the equilibrium position, and finally, the plate approaches monotonically to the stationary position. Okay, so this is a very big difference. And now I show the behavior of the velocity distribution function. Again, this is the marginal integrated over already the molecular velocity component parallel to the boundary. And this is the velocity distribution function of the right side of the plate, and this is the left side, and this is the trajectory. This. And so at the beginning, this is time 0, and both distributions are initial Maxwellian distribution. Then, so now time is 1.4, and so this line corresponds to the velocity of the plate. So this is minus, say, 0.9 or something like that. And this part is the reflected molecules with diffuse reflection. Okay? So this is Maxwellian, but the height is very different on the left side and right side. Okay? And these are the impinging molecules. This is the impinging molecules from the right and the impinging molecule from the left. And this blue, this line is the initial distribution. So this part is different from initial distribution. This means that this part already molecules have undergone recollision. Okay, so such molecules, okay, recollidic molecules. And further, time goes on. I hope it reaches 10. Sometimes it stops in the middle. It stops at 7. This is time 10, like this. And now I will show the longer time behavior. But since this oscillatory part shrinks, I show the magnified figure from minus 0.5 to 0.5. This is minus 0.5 to 0.5, and still magnified figure. Yeah. This very narrow zone from minus 0.03 to 0.03. Then I hope this reaches 100 this time. So distribution function oscillates in this way, and then the oscillatory part shrinks, and so many discontinuities here. Then still slightly the plates it stops at 90. At 100 almost the same. Okay. So this parallel decay is really caused by this part of the velocity distribution function. Okay. If you neglect this, then decay is exponential. So and if you look at the decay of the velocity of the plate, it is natural that if you differentiate this, then you get this one. So this is the observed value. So also the velocity tends to decay with the power minus 3. Okay, so we have shown some piece of numerical evidence that shows decay rate is 1 over t squared, and the velocity decay rate is displacement decays like 1 over t squared, and v 1 over t cubed. Okay, and okay, some numbers I skip, and then okay, I have some little time. Okay, so I quickly move on to the third problem. So this is the original problem. We started with this problem, and then we considered this oscillatory plate case and turns to the equilibrium. But this is the motivation, and this is a disk accelerated by a constant external force. So now I consider the constant external force instead of Hooke's law. Then so suppose that you have a disk, and the external force, constant external force, is acting on the disk, and suppose that it moves freely in the x direction, but no rotation. Then, if you send the plate with the initial velocity v0 at initial time, then if it is slow, then it is accelerated by the external force, and then it reaches a steady motion with constant velocity v infinity, in which the drag and the external force balance. Okay? So So the question is how fast this approach is. And again, if you assume that the drag is proportional to the velocity, then this decay is exponential. But there is a mathematical study already done by Caprino, Marchiolo, Priviletti, and also Cavallaro. They considered this problem with a specular reflection boundary condition. And then they proved the decay rate like this. The velocity decays algebraically with this, and this is the dimension of the disk of the 3D disk, and 2D disk is infinitely long plate in the direction of perpendicular to the screen, and 1D disk is infinitely large, wide plate. Okay? But the condition of the proof is that the difference between the initial velocity and the final velocity should be sufficiently small. How small, I don't know. This is not a physical constraint. It's just a mathematical constraint. And then sometime later, so I was somehow involved in this business at this point. And if you change the boundary condition from specular to diffuse, then exponent change. Okay? So also we are able to prove this decay rate under the assumption that the difference between initial velocity and final velocity is sufficiently small. Okay? So then, so we wanted to confirm this for non-small initial velocity. Okay? So then we did some numerical simulations. So I omit this mathematical proof. And this we have done not a circular cylinder. We have done the plate like this, and 3D, 2D, 1D. And one thing that is not trivial is okay. So here, suppose that no external force is acting on the plate. So if you send the plate, then it stops. Finally, it stops. But this stopping procedure is not obvious, because this is a time and this is a displacement, the position of the plate. Then it reaches the maximum and then it comes back. So it does not stop monotonically. It goes and then slightly comes back and stops. So so this is algebraic. This decay is algebraic. Okay, and but if you neglect the effect of recollision that I mentioned, then the decay is exponential and also decay is monotonic like this. There is a difference. So so the physical explanation of this coming back is like that. So suppose that so this is suppose that this is the initial distribution. I use a G because this is marginal velocity distribution function. It's a Maxwellian initial state, and suppose that the trajectory of the plate is like this, and it stops here, okay? Or almost stopping here. Then if you consider, let us consider the molecules of the same velocity hitting from the right and from the left. Okay? The molecules hitting from the right, you trace back and you reach the initial condition. That is, this is a negative velocity, so something negative value here. The blue arrow corresponds to this velocity in this distribution. So you have this number coming from the right. Okay, but from the left, if you trace back, then you do not reach the initial condition. You reach the point on the trajectory in the past. Okay, so at this point, suppose that the velocity of the plate is v prime here like this. Then only the velocity faster than this velocity can hit the boundary from the left. Then the lift, so this number is not large, small. Therefore, the reflected molecules are small. Therefore, the reflected molecules, this is again half Maxwellian because of the boundary condition, but the height is much lower because this mass conservation between these two. So this height is much lower. Therefore, if you suppose that this molecules come from the initial condition, then you take this value, then the left and right is the same. You have the same amount of particles. But in reality, if the particles are coming from here, then the number is much lower. Therefore, the plate has a much lower momentum from the left, the molecule hitting from the left. Therefore, the plate is exerted by the force which is in the direction of negative x. So therefore, it comes back. So this is the effect of recollision reduces the amount of the molecules hitting from the left. So this is a physical explanation. But we cannot exclude that there is some oscillations and so on. But at least we couldn't see the oscillation numerically. Okay. So in this way, I consider the simplest kinetic equation, but still there are several non-trivial features of that. Okay, thank you very much.
That's a nice talk. Some questions or remarks? Okay, maybe I'm starting. Did you try maybe to use something like DCMC for this relaxation problem?
Yes, first we started this moving plate problem first, and then we tried to do to see the decay rate by DSMC. But it was very difficult because we have to obtain very precise numbers, and so since there is no intermolecular collision, the computation should be easy. Therefore, we can use a huge amount of molecules, particles, but still it was difficult. And then in the middle, we switched to the deterministic solution method.
The same is true for relaxation problems from the first part?
I think it is easier because it is confined in a finite domain. In the other case, it is an infinite domain, but finite in the confined in a finite domain. Therefore, if you use a big number of particles, I think it's possible. But we have not tried.
The domain is not symmetric. So, for example, if you take not a cube but a parallelepiped, what happens is the biggest dimension that drives the
Yes, if one of the dimensions is very large, then maybe at the beginning it behaves something like 2D, like 2D case, and then but a very long time later, finally you get.
the longest dimension.
No, this is just my guess.
If it is not convex, it is really complicated. What happens then?
Yeah, bounded like this.
Yeah.
It should be the same. As the computation becomes more complicated. So, yeah, but I believe that the result would be the same.
Okay. No further remarks? And thank you, Professor.
Thank you very much.